Alright, so in this video we go over section 7.1 integration by parts. Before going over integration by parts, it would be a good idea to review the product rule for differentiation. So consider the product of two functions u and v. Whatever functions they are, alright, if we take the derivative with respect x, we know that we have to differentiate the first one and multiply by the second one plus the derivative of the second one with respect x as well times the first one. I'm going to treat this expression this rule as an equation. I'm going to multiply both sides by dx, okay, and I'm going to cancel the x's everywhere, okay. So we are going to end up with duv equals v du plus u dv. Essentially, I'm taking the differential of a product, not just the derivative, but the differential. Okay. Now I'm going to do this process backwards. Okay. The backwards process would be now to integrate everything on both sides of this equation. Alright. As we may recall, the integral and the differential are opposite operations, so we can just keep this uv, and then these integrals are just integral of v du plus the integral of u dv. Okay, so in this case I'm going to solve for this guy. So for this guy right here, so I am going to subtract the integral of v du from both sides of the equation. Okay, I'm going to cancel these two guys, and I'm going to be left with the integral of u dv equals u times v minus the integral of v du, which is essentially this rule that we have here. Alright, and we are going to run into situations in which we are going to integrate functions that are represented in products, and just like when we did derivatives in the previous course, there is a product rule for taking derivatives, which is what we just reviewed right here. However, there is no such thing as product rule for integration, but it's called integration by parts, in which we are going to actually select the part to integrate. Okay, the best way to have a look at this is by looking at some of the examples. Alright, the trickiest part typically when it comes to integration by parts, it's what to select for u, what to select for dv. Sometimes it's a trial and error, sometimes you do the wrong choice, and then you will be going in circles with the problem. In an effort to keep you from doing those circles, I'm gonna give you the form and the choices. This is already done, this is already proved that it works. Alright, just go with these choices, do not reverse. Okay, keep them like this. Alright, so we have x to the n e to the a x, x to the n ln x, x plus a times x plus b to the n power. As you can tell, we have the product of functions in the integrand. Okay, so we are going to use integration by parts. Okay, let's move on to the next page. Alright, so let's use integration by parts to evaluate these integrals. Letter A, x e to the 3x. Alright, how are we going to choose the u and dv? Alright, So let's refer to our table right here, and in this case it turns out that letter A has the first form in which U will be x and dv the rest of the integrand, which is e to the 3x dx, including the dx. Alright, okay, let me put this on the side so I can give you a better view of this paper. So u we are supposed to differentiate rather to take the differential, and this dv we get v by integrating. Recall that the integral of e to the 3x is going to be 1/3 e to the 3x. Okay, no need to add the plus c. I'm going to talk about it as I go through the examples here. Okay, so the plus c in this case we're going to add it at the very end of the exercise. Okay, so let me recall the formula. Integral of u dv equals u times v minus the integral of v du. This will come in handy when it comes to set up the result. So we're going to multiply u times v, in other words, x times 1/3 e to the 3x, which will result into 1/3 x e to the 3x, minus the integral of v, which is 1/3, du, which is simply dx. Before integrating this, I'm going to take this constant out of the integral. And then I'm going to evaluate this integral just the same way I did it from here when we did the setup for this v dv. Okay, so keep writing 1/3 x to x e to the 3x minus 1/3 times itself another third e to the 3x, and here is the part where we write the plus c. All we do now is simplify these two fractions. So we get 1/3 x e to the 3x minus 1/9 e to the 3x plus c. Final answer for this guy. Alright, let's look at another example. Letter B. Okay, what about letter B? So let's compare letter B with the forms that we have on the table here, and it looks like form B, in which we are going to set u the algebraic part, no, u the logarithmic part, and dv the rest of the integrand, in this case x to whatever power times dx. In this case the whatever power is the number 2 that we have right there. Alright, so can we put this a little bit higher? Okay, so x squared dx. Okay, so let me put this on the side. Now let's take the derivative, or rather the differential of ln x, that is, take du equals 1/x dx, and on the other hand integrate this expression to get v equals 1/3 x to the 3rd power. So now we have all the necessary parts to perform the integration. It would be a good idea to put this inside a box just so it doesn't get confused. Okay, so this is basically the setup. Now let's see. So we're going to multiply ln x times 1/3 x cubed, or rather we write the 1/3, the constant first, the algebraic, and then the logarithmic part. Alright, minus the integral of v, which is 1/3 of x cubed, which in this case I'm going to write it as x cubed over 3 for one reason. You will see, looks a little bit messy, but I'm going to fix that, times du, which is this whole, that whole factor. Alright, so the reason why I wrote it in this form is so we can see how we can cancel this x with one of the powers in the numerator. So in the next step, I'm going to rewrite 1/3 x cubed ln x minus this 3 in the denominator. I'm going to take it outside of the integral as 1/3 times the integral of whatever remains, in this case x squared dx. All that remains is to integrate x squared, which will be, okay, keep writing everything else, minus 1/3 times x cubed over 3 plus c, which will result in 1/3 x cubed ln x minus 1/9 x cubed plus c. Final answer to this. Alright. Now, let's look at another example. So for letter C, let's compare that with the table from the previous page. If we compare, notice how it looks like with letter C from the table precisely, right? So in this case, we are going to take u, the factor that doesn't have any power. Well, there is an invisible power, a power of 1, and dv will be the x plus 4 to the 8th power. So we're going to take the du, which is going to be the x. The derivative of x is 1 times the x is simply the x. And if we integrate this guy, we're going to get v equals add 1 to the exponent divide by that new exponent. Actually, this is supposed to be 9, not 8. Alright. Okay, so let's set up the integral. Let's set up the final result. Okay. So what are we going to get here? We're going to multiply u times v. U times v, which will be x minus 2 times x plus 4 to the 9th power, and this 9 right here, I'm going to write it as a 1/9 minus the integral of v, which is x minus 4 to the 9th power over 9 times du, which is dx. I'm going to take this 9 outside of the integral, so I'm going to have 1/9 times x minus 2 plus 4 minus 1/9 times the integral of x minus, plus 4, not minus, plus 4 to the 9th power dx. All we need is to integrate these guys, so we get equals. Okay, let me box this. One-9 x minus 2 times x plus 4 to the 9th power, I forgot the 9th power, minus 1/9 x plus 4 to the 10th power using a baby substitution divided by 10 plus c. Now let's multiply this 9 times 10 to get 1/9 x minus 2 x plus 4 to the 9th power minus 1/90 x plus 4 to the 10th power plus c. Final answer. Alright, let's do one more. Letter D. Okay, letter D, it might look a little bit tricky at first. Alright, because in the forms that we had on the table on the previous page, we didn't have anything with radicals. However, I will rewrite the integral first with rational exponents. Okay. And then I'm going to move this with negative exponent to the numerator. Okay. dx. Alright, so in this case, this integral is going to look like the previous one, right? So, but okay, can we do this when we have rational exponents or even negative? Yes. On the box in the previous page, there is no restriction about this value of n. So it can be very well a negative number or a rational number, right? That doesn't make any difference. We can use this for the integration. So let's set u equals x. It's like having x minus 0 or x plus 0, and dv equals to x plus 4 to the negative 1/2. Alright, so what are we going to have? So the du will be dx. Integrate this guy, we get v equals, to integrate this by substitution, well, in this case, add 1 to the exponent, x plus 4 to the negative 1/2 plus 1, that's going to give us positive 1/2 divided by 1/2. But this is kind of messy to read, so v is going to be 2 times x plus 4 to the 1/2. I know what you're thinking at this point. Maybe we can go back and rewrite this in radical form. Yes, we're going to do that soon. Okay, so now these are the parts for the setup. Let me put them in a box. And let me write down the result. So u times v, that is, it's going to be 2x times x plus 4 to the 1/2 minus the integral of v du, which in this case is 2x plus 4 to the 1/2 du, which is dx. So the first term we can go back and write it, or just leave it like this. Either way is fine. I'm going to leave it like this. 2x times x plus 4 to the 1/2 minus 2 times the integral. I'm just going to take the constant out of the integral. So the next thing is to integrate this by substitution. No need to show the work because this is a 1. So add 1 to 1/2. We're going to get 3/2. Plus 4 to the 3/2 divided by 3/2 plus c. I'm not going to leave this like this. I'm going to take care of this 3/2. That is the same as multiplying by the reciprocal, which is 2/3, or multiply the 2 with the 2 and keep the 3 in the denominator, or otherwise. So we get the same here, minus 4/3 of x plus 4 to the 3/2 plus c. Final answer. So these are a few short and simpler examples in which we apply integration by parts. Alright, what else can we do with integration by parts? So we can do repeated integration by parts. Alright, sometimes it is necessary to iterate or reiterate the process of integration by parts. As we've seen before from the first page, okay, let me put it back again. So we have x to the n e to the ax, which matches the first form. So I'm going to let that u equals x squared and dv to be e to the 4x dx. Okay. Now let's do the same that we did before. Du will be in this case 2x dx, and v, which will be the integral of this, which will be 1/4 e to the 4x. Again, no need to write the plus c. Let's put this inside a box. Alright. So let's use a formula for integration by parts. U times v, that's going to give us 1/4 x squared e to the 4x minus the integral of v, which is 1/4 e to the 4x times du, which is 2x dx. So there's a few things that we will need to do here. Number one, I'm going to simplify 2/4, which will be 1/2, and at the same time I'm going to write it outside of the integral. X e to the 4x dx. Alright? So now, if you look at this form, let's ignore everything else. Here, we have an integral that requires to do integration by parts a second time. And that's what I will do here. I'm going to do the work to take another u, which in this case is going to be x, and the dv, which will be e to the 4x dx. So this one we already did it, that's 1/4 e to the 4x, and du will be dx. Let's put this in a box. Alright, so what are we going to have here? We keep going. The first term we could just keep writing it. 1/4 x squared e to the 4x minus 1/2 times, I'm going to open bracket here, open brackets, and write whatever the result from doing the integration by parts. Some textbooks or some other resources typically keep the constant inside and carry that constant, like the 1/2 here, within the setup. But notice how here we don't mess with too many constants. In my personal opinion, it's more efficient to work this way and just save this negative 1/2 to later distribute it. However, if you want to do it the other way around, that's up to you. You should get the same answer. Alright, so it's going to be u times v, which is 1/4 times x e to the 4x minus the integral of v, which is 1/4 e to the 4x du, which is dx. Let me make this guy look like an x. Alright. And close the brackets. That's 1/4 x squared e to the 4x minus, first of all, what am I going to do? I'm going to distribute 1/2 times 1/4. That's going to give me 1/8 x e to the 4x, and over here be very careful, negative 1/2 times this 1/4 that I would have rather have outside. That's going to give me negative times a negative, positive 1/8 times the integral of e to the 4x dx. So now all we need to do, well, ignore this constant for a second, just evaluate the integral from the integral of e to the 4x. So we are going to have 1/4 x squared e to the 4x minus 1/8 x e to the 4x plus 1/8 times 1/4 e to the 4x plus c. All we need to do now is multiply this 4 times 8 in the denominator to obtain, okay, keep writing the what we had from before, and then just have 1/32 e to the 4x plus c. Final answer. So in this case, a very important, or rather a very interesting pattern about integration by parts when it comes to repeated ones. Notice how did we do 1, 2 times the integration by part that is based on the power that we have for x to the n e to the 4x. Alright, so I think that's a very interesting pattern to consider. So for example, if you see x to the 5, x to the 5th, e to the 7x, good luck, be prepared to do integration by parts 5 times. Is it gonna be fun? Maybe not. After a while it's not fun. Actually, if you look at this one, I think doing it twice is more than enough. It's more than a good exercise. Even 3, it's a good exercise as well, maybe in the homework. Okay, the last example for this section is how to do definite integrals using integration by parts. Okay, so I'm going to choose a simple integral like the one we already did. U equals x dv equals e to the 3x. So du in this case is dx, and v is 1/3 e to the 3x. So this we already did in the previous examples. Really, the purpose of this exercise is to show you how to express or how to denote the results for every time that we get the integration. So u times v, that's 1/3 x e to the 3x. And in this case, since we are done with the integral for that part, we do 1 to 2. We write down the bars, evaluate it. We indicate that we evaluate this integral from 1 to 2 minus the integral from 1 to 2 of v, which is 1/3, du, which is dx. So do not evaluate upper minus lower yet. We're going to leave that for the end. So we're going to have 1/3 x e to the 3x minus 1/3 times the integral of it to the 3x, which is also 1/3 e to the 3x. The whole thing evaluated from 1 to 2. Notice I didn't write it over here the same way I did write it, because as long as we write it at the end, because it corresponds for everything, that's good enough. So 1/3 x e to the 3x minus 1/9 e to the 3x evaluated from 1 to 2. Alright. So now it's time to apply the fundamental theorem of calculus and evaluate upper limit minus lower limit. So in this case, I'm going to do 1/3 the upper limit, which will be 2 e to the 3 times 2 minus 1/9 e to the 3 times 2 alright, in brackets preferably, minus brackets, we do the same, 1/3 and then 1 evaluated at 1. Alright, so let's simplify this operation. So we're gonna have 2/3 e to the 6th minus 1/9 e to the 6 minus 1/3 e to the 3rd minus 1/9 e to the 3rd. Alright, so in this case, notice how these two are like terms because they are both e to the 3rd, and these two are like terms because they are e to the 6th. So in this case, I'm going to multiply by 3, numerator and denominator, to have the same denominator. That's going to give me 3 times 2, which is going to be 6, but 6 minus 1, it's going to be 5/9 e to the 6th. And then over here I'm going to have 3 times 1, which is 3. 3 minus 1, that's going to give me 3 minus 1 is 2/9 e to the 3rd. Final answer. So this is it for this video. I'll see you in the next section.